Module 2, Lecture A, Conditional Checks. By the end of this lecture, you will be able to write Boolean expressions that compare calculated values with engineering limits, use if, elif, and else statements to classify civil engineering conditions, and create clear warning messages for results that exceed specified criteria. Boolean logic. Compare engineering limits. Boolean logic helps engineers turn design checks into clear, true or false decisions. In civil engineering, results such as stress, load, or deflection must be compared with required limits, like capacity or safety criteria. These comparisons show whether a structure meets the necessary conditions. Engineering limit checks must match the meaning of the limit. For maximum limits, the calculated value should be less than or equal to the allowable value, while for minimum requirements, it should be greater than or equal to the required value. Reversing this comparison can change the result and lead to the wrong engineering judgment, so the check must reflect the design's physical intent. In engineering Boolean comparisons, make sure the calculated result and the limit use the same units and accurate values. Because calculations can include approximations and uncertainty, a result that barely passes may still need review. Boolean logic supports consistent decisions, but it does not replace professional judgment. Python code. Compare engineering limits. When checking calculations against engineering limits, use Boolean comparisons that produce either true or false. Before making any comparison, make sure the units are consistent, so the result is meaningful. The beam's calculated deflection is set at 18 millimeters, while the allowable deflection is 20 millimeters. These values are used to check whether the beam stays within the acceptable deflection limit. This check compares the beam's actual deflection with the allowable limit. If the deflection is within that limit, the beam passes the serviceability check. If it exceeds the limit, the result indicates a possible serviceability problem. The slope's current factor of safety is set at 1.35, while the required minimum is 1.50. These values will be compared to check whether the slope meets the needed stability and safety standard. This check compares the current slope factor of safety with the required minimum value. If the current value meets or exceeds the requirement, the slope is considered stable. If it falls below the requirement, the result indicates a possible stability concern. The bridge clearance is measured at 14.2 feet, while the required minimum clearance is 14 feet. These values allow us to check whether the bridge meets the needed safety standard. This code checks whether a bridge has enough clearance by comparing the actual clearance with the required minimum. If the actual clearance is at least the required amount, the check returns true, meaning the clearance is acceptable. If not, it returns false, indicating a possible clearance problem. The code reports the results of 3 engineering checks: beam deflection, slope safety factor, and bridge clearance. Each output states whether the design meets the required limit, giving a concise pass or fail decision. This step checks whether the beam's deflection stays within the allowable limit. If it exceeds that limit, a warning is shown to indicate a potential problem that needs attention. The code checks whether the slope's factor of safety is below the required level. If it is too low, it prints a warning so the issue can be reviewed. The program checks whether the bridge clearance meets the required minimum. If it does not, it prints a warning, so the clearance issue can be identified and addressed. The code summarizes whether the design is acceptable by checking that the deflection, safety, and clearance requirements all pass. It combines these results so the overall approval is true only when every limit is satisfied. It then prints a clear message showing whether the design meets all required engineering checks. This script checks whether key engineering design criteria meet their required limits. It compares beam deflection, slope safety factor, and bridge clearance against acceptable thresholds, reports which checks pass, and warns if any fail. It then gives an overall pass or fail summary for the design. Compare engineering limits. In civil engineering, Boolean comparisons help turn calculations into decisions by showing whether a result meets a required limit. Engineers use true or false checks to judge issues such as beam deflection or column stress against performance and safety criteria. This makes Boolean logic essential for connecting numerical analysis to practical engineering judgment. In engineering comparisons, the logic must match the design goal and the physical meaning of the limit. A maximum limit checks whether a value stays below an allowed upper bound, while a minimum requirement checks whether it reaches the needed threshold. Always identify whether the constraint is an upper limit, lower limit, or acceptable range, so the result reflects the real engineering condition rather than just a numerical comparison. Engineering limits usually come from standards, specifications, or design decisions, and calculated results must be compared with them carefully. True or false checks can help screen designs, flag problems, and support consistent decisions, but their meaning depends on context. Clear Boolean logic can expose unsafe or inefficient conditions early, while poor logic can hide issues or create false confidence. Python code. Compare engineering limits. Boolean checks compare results against engineering limits to produce true or false decisions. Clear comparisons help engineers make safe, reliable design judgments. We record the beam's deflection as 18 millimeters and the allowable limit as 20 millimeters. These values can then be compared to check whether the beam stays within acceptable safety and performance limits. The beam's deflection, measured in millimeters, is checked against the allowable limit. If the deflection is less than or equal to that limit, it is considered acceptable, and a message reports whether the beam meets the requirement. The slope's calculated safety factor is 1.42, while the required minimum is 1.50. These two values are stored so they can be compared to determine whether the slope meets the required stability standard. Check slope safety by comparing the current factor of safety with the required minimum. If the current value is at least as high as the requirement, the slope is considered acceptable, and the result is reported. The estimated foundation settlement is 1.25 inches, while the allowable settlement is 1.00 inch. These values are used to check whether the actual or predicted settlement is greater than the safe, acceptable limit. The code checks whether the estimated foundation settlement is greater than the allowable limit. It stores the true or false result of this comparison, then prints a message showing whether the limit has been exceeded. The pipe's fluid velocity is set to 2.4 meters per second. This is checked against an acceptable range from 0.6 to 3 meters per second to determine whether the flow velocity is within limits. The code checks whether the pipe velocity stays within the allowed minimum and maximum limits. It stores the result of that comparison and then prints a message saying whether the velocity is acceptable for safe operation. The code determines whether an engineering warning is needed by checking two safety conditions: excessive foundation settlement and an inadequate slope safety factor. If either condition fails, it marks that a warning is required and prints the result. The script checks several engineering conditions against their allowable limits. Beam deflection and pipe velocity are acceptable, but the slope safety factor is too low, and the foundation settlement is too high. Because at least one critical condition fails, the script concludes that an engineering warning is needed. Threshold checks. In civil engineering, threshold checks use true or false logic to decide whether a calculated value stays within an acceptable limit. Engineers compare results such as stress, deflection, or flow velocity with design criteria to identify safe versus unsafe, or acceptable versus unacceptable conditions. The key purpose is to determine whether a result crosses a critical boundary, not simply to calculate the value. When defining a threshold check, make sure the comparison matches the engineering purpose. For maximum limits, values above the threshold indicate a problem, while for minimum limits, values below the threshold are the concern. State the condition clearly so reviewers can quickly understand what is being checked and why it matters. Threshold checks near engineering limits require more than simple comparison. Measurement uncertainty, changing conditions, and the purpose of the check can affect how values should be interpreted. Boolean logic can organize the decision, but engineers must choose limits carefully, whether they need a strict boundary or a warning range. Done well, these checks turn technical criteria into clear, consistent, and defensible decisions. Python code. Threshold checks. Threshold equals 10. Value equals get input. If value equals threshold, print exceeds threshold. Else, below threshold. Compare engineering values against their limits using Boolean checks that return true or false. Clear result messages make these checks easier to understand during design review. The stored engineering values include a beam deflection of 18 millimeters and an allowable limit of 20 millimeters, which will be used to judge whether the beam stays within safe bending limits. A pipe velocity of 1.8 feet per second is also stored to represent the fluid flow speed. These values provide the basis for later criteria checks. The design sets 3 key limits for later checks: a minimum pipe velocity of 2 feet per second, an actual factor of safety of 1.65, and a required factor of safety of 1.5. Together, these values help confirm that the system provides adequate flow and meets the required safety standard. The engineering checks compare each measured value against its required limit and return a true or false result. Beam deflection must stay below the allowable maximum. Pipe velocity must meet the minimum speed, and the factor of safety must reach the required level. Together, these Boolean checks quickly show whether the design values are acceptable. The code prints a short summary of threshold checks for civil engineering values. It reports whether beam deflection is acceptable, whether pipe velocity meets the minimum requirement, and whether the factor of safety satisfies its required limit. Together, these messages clearly show the outcome of each condition. The code checks key design limits in order of priority. It first warns if beam deflection is too high, then warns if pipe velocity is below the required minimum. If both checks pass, it reports that the main checks are acceptable, while reminding the user to review the safety factors separately. After serviceability is checked, the code evaluates the safety factor and reports whether it meets the required level. If it fails, a warning clearly indicates that the factor of safety is too low. The code prints the final safety status message, which was set earlier based on whether the factor of safety meets the required threshold. This gives the user a clear indication of whether the engineering design satisfies the safety criteria. This script checks key engineering values against required limits and prints clear pass or warning messages. It verifies whether beam deflection is acceptable, pipe velocity is high enough, and the factor of safety meets the standard. If the main checks pass, it still reminds the user to review the safety factor separately, helping ensure critical design parameters are assessed efficiently. Branching rules. If statement basics. An if statement lets a program choose what to do based on whether a condition is true or false. In civil engineering, it can trigger actions when a calculated value such as settlement or slope angle exceeds an acceptable limit. This is important because engineering decisions often depend on interpreting calculation results, not just producing numbers. An if statement lets a program choose what to do based on a condition, instead of always running instructions in the same fixed order. This allows the program to respond to the data it is processing, such as flagging a pavement location when rut depth is too high. The same idea is used across engineering when checks like load limits or safety conditions require specific actions. An if statement should use a precise condition and a clear action. The condition should be based on defined engineering standards or project requirements, such as a displacement exceeding a monitoring limit, rather than a vague judgment. The action should also be specific, such as flagging a record for review or requiring further analysis. This helps ensure consistent decisions and reduces misinterpretation. Python code, if statement basics. This example shows a simple engineering decision. Compare rut depth with a maintenance limit, and run the decision block only if the condition is true. The measured pavement rut depth is 0.72 inches, while the allowable limit is 0.50 inches. These values are compared to determine whether the rut exceeds the maintenance threshold and requires action. The code announces a pavement rut depth check and reports the measured rut depth to 2 decimal places for clear review. The code compares the measured rut depth with the allowed limit. If the rut depth is too high, it warns that the maintenance threshold has been exceeded. This helps decide whether maintenance is needed based on engineering criteria. After the conditional logic runs, a print statement confirms that the if statement check is complete. This shows that the program has finished evaluating the condition and continued past the decision point. This script checks whether a measured pavement rut depth is above the maintenance limit. It compares a rut depth of 0.72 inches with an allowable limit of ½ inch, then prints the measurement and the result of the check. Because the measured rut depth is greater than the limit, the script prints a warning that maintenance attention is needed. Else classification. An else statement provides the default action when a condition is not met, ensuring every case is handled. In civil engineering, it can classify results such as acceptable or outside limits. For example, if pavement deflection stays below a threshold, the else path can mark it as acceptable. An else statement makes decision logic complete by clearly defining what happens when the main condition is not met. In engineering work, this helps avoid ambiguity in tasks such as inspections, design reviews, slope stability checks, and stormwater assessments. The else path should be treated as an intentional category, such as not urgent or normal operation, so results are clearer and easier to act on. Use else statements carefully, so every unmatched case has a clear outcome. The conditions before the final else should be specific enough to avoid grouping situations that need different responses. In engineering contexts such as bridge inspections, it is better to define detailed categories first, then use else only as a reliable final case. Python code, Else classification. Else branches help complete engineering decisions by defining what happens when earlier conditions are not met. In this example, they support a short, clear classification of pavement deflection. The measured pavement deflection is 7.4 millimeters, and the allowable limit is 8.0 millimeters. These values are compared to decide whether the pavement deflection meets the acceptable engineering standard or exceeds it. We check whether the measured deflection is greater than the allowable limit. The result is true if the limit is exceeded, and false if the deflection stays within the allowed range. The deflection measurement is compared with the allowable limit to determine pavement status. If it is too high, the status gives a warning. If not, it confirms the deflection is acceptable. This clearly classifies each measurement based on the threshold. The output reports the measured pavement deflection in millimeters, then shows the allowable deflection limit for comparison. It then gives the pavement status based on whether the measured value exceeds that limit, providing a brief engineering assessment. The script checks pavement deflection by comparing a measured value of 7.4 millimeters with an allowable limit of 8 millimeters. Since the measured deflection is below the limit, the result confirms that the deflection is acceptable. It also prints both values before showing the final classification. Elif-else paths. In civil engineering programs, an else-if path helps handle decisions with several possible outcomes. For example, pavement condition can be checked in order from good to failed, and the first matching category guides inspection or maintenance actions. Once a condition is met, the program skips the remaining checks, making the logic efficient, clear, and reliable for planning and safety decisions. In an else-if path, condition order matters because the program checks from top to bottom and stops at the first match. Put the most specific or critical conditions first, so they are not missed by broader ones. In engineering decisions, this helps ensure serious cases, such as extreme rainfall or very low concrete strength, receive the right response before less urgent cases are considered. The final else branch provides a default outcome when no earlier condition is met. In engineering classification tasks, it can mark a normal case, such as a stable slope, or flag unexpected inputs, such as unusual bridge clearance values, for verification. This ensures every input produces a clear and actionable result. Python code. Elif-else paths. Use ordered conditional branches to classify stormwater rainfall, since each branch selects the first condition that is true. Clear classification messages help support practical engineering decisions. The rainfall intensity is set to 72 millimeters per hour. This measured value is used to compare against predefined thresholds and classify the severity of the rainfall event for stormwater response. Stormwater response thresholds are set by rainfall intensity. A watch limit of 25 triggers routine monitoring. A warning limit of 50 calls for urgent drainage inspection, and a closure limit of 75 requires immediate closure review. These levels help classify storm severity and guide the appropriate response. The code reports the current rainfall intensity in millimeters per hour, giving engineers a quick measure of how severe the rain is. This helps them compare conditions against set thresholds and make informed decisions. The code first checks whether rainfall intensity has reached the closure limit, because this is the most serious condition. If it has, the status is set to require an immediate closure review, ensuring the highest safety risk is handled right away. This part checks whether rainfall intensity has reached the warning limit. If it has, the status is set to require an urgent drainage inspection. This handles serious rainfall levels that may cause drainage problems, while reserving stronger actions for more severe conditions. The conditional structure keeps the decisions organized in priority order. This branch checks whether rainfall intensity has reached the watch limit. If so, it sets the status to recommend routine monitoring. Because it runs only after earlier conditions fail, the code chooses the first matching action for the current rainfall level. The else branch handles the default case when rainfall stays below the watch limit. It sets the status to show that no stormwater action is needed, ensuring the program always provides a clear result, even for minimal rainfall. The code displays the rainfall classification result by using the message selected from the first true condition. This gives a clear alert level or recommended action for the current rainfall intensity. In Python, an if, elif, else structure runs only the first branch whose condition is true. Once that condition is found, the remaining checks are skipped. This keeps decisions clear and efficient by choosing the first relevant action, such as in stormwater management logic. The script compares the current rainfall intensity with preset watch, warning, and closure thresholds to choose a stormwater response. At 72 millimeters per hour, the rainfall is above the warning level but below the closure level, so it classifies the situation as requiring urgent drainage inspection. Because Python stops at the first true condition in this decision chain, only the most severe applicable action is selected. Engineering warning criteria. Warning messages. Warning messages help turn limit violations into clear, practical guidance for engineers and decision makers. In civil engineering, they may flag problems such as excessive beam deflection or water levels above a flood threshold. An effective warning states what happened, how serious it is, and why action is needed. Because vague messages can delay responses and increase safety or performance risks. Warning messages should be tailored to the user's role and level of detail needed. Engineers may need specific component or standard information, while supervisors may only need a clear indication that a threshold was exceeded. Each warning should connect the condition to the relevant engineering standard and distinguish minor issues from critical risks, so users can respond appropriately. A good engineering warning message clearly explains what limit was exceeded, where it occurred, and why it matters. By turning technical checks into concise, precise, and understandable alerts, it helps teams document issues and choose appropriate actions. The tone should stay calm and actionable, supporting quality control and safety decisions without creating unnecessary alarm. Python code. Warning messages. Clear warnings help engineers react quickly when results exceed limits. Conditional checks should compare results against defined criteria, and the warning message should clearly state which criterion was exceeded. A calculated beam deflection of 1.15 inches is stored to represent how much the beam bends under load. This value will be compared with an allowable limit to decide whether the deflection is acceptable. The code defines a serviceability deflection limit of 0.9 inches. This sets the maximum acceptable deflection for a structural member, so later calculations can be checked against the allowed performance threshold. The code stores the name beam B12 in a variable to identify the structural member being checked for deflection. This makes it easier to refer to the same member consistently in reports or later calculations. The code compares the beam deflection to the serviceability limit. If the deflection is too high, it identifies that the acceptable level has been exceeded and issues a warning. The code creates a warning message for engineers about beam B12. It reports the member's deflection to 2 decimal places and clearly states that the value exceeds the serviceability limit. The code adds the deflection limit in inches to a status message and formats the value to 2 decimal places for clarity. This message is used with either a warning or an acceptable result, depending on whether the actual deflection exceeds the serviceability limit. This section handles the case where the beam's deflection is acceptable. When the earlier condition is not met, the program creates a message saying the beam is within the serviceability limit. The message includes the beam name, the measured deflection, and the allowed limit to clearly confirm that the result is within range. The code creates a clear status message showing that a beam's deflection is acceptable. It uses formatted text to include the member name, the measured deflection rounded to 2 decimal places, and the serviceability limit. The result is a concise confirmation that the deflection check has passed. The code creates a clear message about a beam's deflection limit, showing the limit value rounded to 2 decimal places. It is used inside a condition that determines whether the beam's deflection exceeds its allowable serviceability limit. The message helps communicate whether the beam's deflection is acceptable. The program displays a message reporting whether the beam's deflection is within the allowed limit or exceeds it. That message is created from an earlier comparison between the actual deflection and the acceptable limit, giving immediate feedback on the structural check. The script checks whether a beam's deflection stays within its serviceability limit. It compares the measured deflection with the allowed limit, then reports either that the beam complies or that it exceeds the limit by a specified amount. The printed result clearly shows whether the beam's deflection is acceptable or needs attention. Limit exceedance alerts. Limit exceedance alerts show when a calculated value goes beyond an engineering limit, such as allowable stress, load capacity, pavement deflection, or wall movement. They should make the practical consequence clear, not just flag a number, so engineers understand the risk and know when further investigation or action is needed. Effective limit exceedance alerts should clearly state which engineering limit was breached, what measured result triggered it, and what condition it indicates. Instead of vague wording, identify the relevant parameter, such as deflection, load, strain, or concrete strength, and explain how it compares with the required threshold. Clear alerts let users understand the issue quickly and make decisions without checking raw data or recalculating results. Limit exceedance alerts help teams make fast, safe engineering decisions, especially when different roles may interpret the same data in different ways. Effective alerts use clear, consistent language, include key context such as location, and connect the warning directly to its engineering impact. Whether addressing flood levels or rainfall linked to slope and stability, the alert should show the urgency and guide appropriate monitoring or action. Python code, limit exceedance alerts. Conditional alerts warn when engineering limits are exceeded. Effective warnings state the measured value, the limit, and the likely consequence, as in checks of several civil engineering measurements. A list of checks stores engineering measurements in a structured way. Each entry includes the measurement description, the measured value, the allowable limit, the unit, and the consequence of exceeding that limit. This makes it easy to review each measurement, compare it with its limit, and generate alerts when needed. The code prints the heading Limit Exceedance Alerts to introduce the output. It tells the reader that the following information will identify engineering measurements that are above their allowed limits. The code checks each measurement against its limit to assign an alert level. Values above the limit are marked as a warning. Values exactly at the limit are marked as caution, and values below the limit are marked as OK. This provides a simple way to classify each measurement by severity. The code builds a concise status message for an engineering check. It reports whether the measurement is OK, a caution, or a warning, then gives the measurement name, its current value in unit, the limit for comparison, and the related consequence. This helps the reader quickly understand the condition and any needed concern or action. The code prints a concise console alert about an engineering measurement. The message reports the measurement status, name, current value with units, comparison limit, and the consequence of exceeding that limit, so key engineering constraints are easy to understand quickly. This line counts how many results are above their allowed limits. It checks each value against its limit and adds 1 for every case where the value is too high, giving the total number of results that need attention. The code creates and prints a short summary showing how many engineering checks exceeded their limits. By reporting the total number of exceedances, it helps engineers quickly see how many alerts need attention. The script checks key engineering measurements against their allowed limits for beam deflection, wall movement, and channel depth. It labels each result as OK, caution, or warning, depending on whether the measurement is below, equal to, or above the limit. It then reports the status and consequence for each case and gives a final count of exceedances that need attention. Clear warning messages. A clear engineering warning should explain what was detected, why it matters, and what action is needed. In civil engineering, this means turning numerical limit violations, such as excessive stress or deflection, into plain guidance that identifies the affected part and recommends review or inspection. Clear messages help engineers and inspectors respond correctly, especially under time pressure, or when several people must interpret the same data. Warning messages should be clear, specific, and concise enough to guide action. Instead of vague alerts, state the problem, where it occurs, the measured value, the limit, and how serious it is. This helps users quickly distinguish minor issues from critical ones, such as flood risks in stormwater design or low concrete strength in construction quality control. Warning messages should be professional, direct, and matched to the seriousness of the issue. They should avoid blame or emotional language while clearly guiding users toward the right action, such as requesting engineering review when a slope stability check raises a safety concern. Consistent wording helps users interpret alerts reliably and connects numerical results to practical decisions and records. Python code, clear warning messages. Clear engineering messages should link each check to a specific action. In this example, values are compared against stated limits, and each warning identifies the condition, the measured value, and the required response. The bridge girder's measured deflection is recorded as 38 millimeters, while the allowable limit is set at 25 millimeters. These two values provide the basis for checking whether the bridge deflection meets engineering standards. The wall's observed safety factor from inspection is 1.25, while the required minimum is 1.5. Comparing these values shows whether the wall meets the stability standard and whether engineering action may be needed. The code compares the bridge girder deflection with the allowable limit. If the deflection is too high, it prints a warning with the measured value and the limit, indicating that engineering review is needed. If the deflection is within the limit, it reports that the girder deflection is acceptable. The wall's safety factor is compared with the required minimum. If it is too low, a warning is given, so stability can be reviewed before continuing. If it meets the requirement, a confirmation message indicates that the wall's safety factor is adequate. The message emphasizes that warnings should be clear and actionable. A useful warning identifies the affected component, states the result, notes the limit involved, and explains any needed action so engineers can quickly understand and address the issue. This script checks engineering values against set limits and warns when action is needed. It flags excessive bridge girder deflection for engineering review and a retaining wall safety factor below the minimum for stability review. Each warning clearly states the issue, the measured value, the limit, and the required response. In this lecture, you learned to write Boolean expressions that compare calculated values with engineering limits, use if, elif, and else statements to classify civil engineering conditions, and create clear warning messages for results that exceed specified criteria. In the next lecture, Lecture B, we will go over loops and iteration.
Thank you for your attention. See you all in the next lecture.